From the computer science department at Rutgers of polynomial-graphy. Polynomial-graphy same. We will speak about something else, solving linear systems of equations by a convex Hull algorithm.
Thank you very much, Laurent. It's a pleasure. Actually, as Professor Zeilberger mentioned, I have interest in polynomial root finding, and ironically, this work, which is on something else, was somehow directly was inspired by my interest from root finding. I don't have much time to talk about how exactly, but I like to talk about solving linear systems, which everybody is interested in or very applied, from a different point of view. So, of course, if you have a real matrix n by n, let's say invertible matrix, to solve it, we do the LU factorization, and then forward and backward substitution. If, let's say, there is no permutation of the rows, we solve it, and the complexity is of n-cubed arithmetic operations. Suppose that each AI is a rational number with at most L bits. Then each arithmetic operation has a complexity polynomial in L. For instance, multiplication can be done in O of L, log L, log L, Schroningen, Strassen. Edmonds is credited to be the first one who showed that Gaussian elimination is actually polynomial-time. So we do n-cubed arithmetic operations over O of L-bit numbers. If the matrix is not a square one, say m by n, then of course we can still do it in polynomial in m and n over O of L-bit numbers. Now what happens if you have a system of the type ax equals to b, x bigger than or equal to 0, which is the linear programming feasibility problem? How do we solve this? This is linear programming feasibility. The best known algorithms for solving this require arithmetic operations polynomial in m and L, say q of m and L, over O of L bits. So the difference between solving this system and linear programming and linear systems is that this L plays a role in the number of iterations that is carried out. It is not known if a strongly polynomial-time algorithm exists for this problem. That is, an algorithm that runs in polynomial time in m and n over O of L-bit numbers. Linear programming in standard form is an optimization problem, actually, say minimization over a system ax equals to b, x bigger than or equal to 0. It is assumed that this is feasible and a basic feasible solution is available, which is a solution with n minus m of the components 0, and the remaining is determined by an m by m linear system, bx equals to b. Bx equals to b. It's an m by m, b is an m by m invertible submatrix. The Danzig's algorithm, which is the best known algorithm for a simplex method, moves from one basic feasible solution to another. Clementi example showed that it requires an exponential number of iterations in the worst case. To find a solution to ax equals to b, which is a feasibility problem, simplex method needs to convert it into a linear programming. So this is like phase one. And of course, through known duality theory, we can convert an optimization problem into a feasibility problem. Solving linear systems in linear programming, whether or not we solve LP as an optimization problem or as a feasibility problem via the simplex method or other polynomial time methods, we need to solve linear systems. And a linear system, we can solve it by iterative methods as well as things like methods such as Gaussian elimination. These are the classical methods, Jacobi, Gauss-Seidel, SOR, conjugate direction. What I like to do is to go to reverse this process. That is, solving Ax equals to b, I want to solve it as a special LP problem, reversing the process. So the special problem that I will consider is a convex Hull problem. And the convex Hull problem is a very simple problem to state. We are given a subset of n points in R to the m and a distinguished point P. And we like to see if P lies in the convex Hull of these points. P is in the convex Hull if and only if it can be written as a convex combination here. So to determine if a point is in the convex Hull, we must somehow compute these multipliers, alpha i's. Remark, I want to tell you how important this problem is. First of all, it's probably the most fundamental problem in convex Hull. This book on computational geometry talks about it. It's a special case of linear feasibility problem. Also, in 1984, Karmakar introduced a new algorithm which was a very important polynomial-time algorithm for linear programming. And really, although he didn't say it, he's trying to solve the convex Hull problem. In 1979, Khachiyan introduced the ellipsoid method, first polynomial-time algorithm. And his algorithm also solves the convex Hull problem, but in a dual form. He didn't also mention that. But that's how important this problem is. You can define an approximate version of this convex Hull. First of all, let the UV stand for the Euclidean distance. An epsilon approximate version of this problem P, the convex Hull problem, is that given epsilon, either compute a point p sub epsilon in the convex Hull such that the gap between p epsilon and p is bounded by epsilon times the maximum of the distances of p to the other points, to the VIs, or prove that p is not in the convex Hull. Now, for integer inputs, a sufficiently small epsilon approximate solution can be rounded into an exact solution. So all polynomial-time algorithms would come up with a process that would sort of massage this approximate solution into an exact one. Now, in this talk, the outline of this talk is applications and significance of LP, the triangle algorithm for solving LP and its complexity, a new characterization theorem for what I call distance duality, application of it in linear programming, comparison to some existing algorithm, application of a triangle algorithm to solving Ax equals to b. So really I'm combining two papers, two talks into this one. Some other applications. First of all, why is problem P, this convex Hull problem, is so significant? It's the most fundamental problem in convex Hull problem, in all of probably math or computational geometry. It's the most fundamental problem in linear programming. It finds applications in approximation theory, machine learning, and statistics, and more. Either implicitly or explicitly, all the polynomial-time algorithms, the most famous of them, have been designed to solve this problem. Furthermore, if there is a strongly polynomial-time algorithm for linear programming, probably this is the best candidate to look at. I wouldn't be surprised if such algorithm is found. This is the problem that a person is considering. And problem P has given rise to new algorithms and dualities, and I'm going to talk about one today. Now here is problem P for a triangle. Suppose that we know the coordinates of the VIs, and we know the point P is in the convex Hull of these. I want to figure out those multipliers, alpha i's. But one way of doing it is you form this system. You write the coordinates, and we have 1, 1, 1, right? So we solve this linear system. But this would be completely ignoring the fact that this point is in the convex Hull. So the triangle algorithm, I want to introduce you to this algorithm. And if probably there is anything that I would like you to remember from this talk, is this triangle algorithm, which says you start with a set of points, and you want to know if P is in the convex hull of these. So what do? Given P prime in the convex hull, check if there is a Vj such that the distance between P prime and Vj is bigger than or equal to this. We call such a point a pivot point. If no such point Vj exists, then this inequality is satisfied for all I. We call such a P prime a witness. Step 2, otherwise, on the line segment, connect P prime to Vj if this is if this happens, and then compute the point P double prime which is closest to P. Replace P with P double prime and go to step 1. I'm going to show you how this works on a triangle actually. So I use this pivot point as an auxiliary point to get closer to to P. The justification behind this name, why did I say triangle algorithm? Because it's in every iteration it's between P and a Vj, which is a pivot point, and P prime. So there are only 3 things involved here to find the next iterative. If such a triangle exists, then Vj is used as a pivot point to come closer to the point. So let me explain this for the triangle algorithm for the triangle itself. Here is P. I want to know if P is in the convex hull or not. I only know the coordinates of P. I know the coordinates of VRs. Okay? So I can start with a point P prime which is inside. Simply pick a point whose coordinates add up to 1. Alpha 1, V1 plus alpha 2. And this P prime, like we hire this person, P prime. He's an inside man. He's really Spider-Man. Why? Because he's going to look at these 3 vertices and see if he finds one that is farther away to him than P is. So in this case, he finds P prime. Then he's going to throw his web to that point and pull himself closer. So he's not here. Okay? In one iteration. The next iteration, we are there. Not bad, right? We're getting close in 2 iterations. And let's take a situation where P is outside. And take the same iterate P prime. He throws the web at V3. In this case, the closest point happens to be V3 itself along this direction. So P double prime, the new iterate becomes P double prime. Now, from P double prime, he tries to find a pivot point, which is V2. He comes closer, and now he can witness that P is outside. So that's the algorithm, as simple as that. Now, if you put P, you can play with this yourself and try it with a triangle or a square. You get interesting situations. Actually, even visualization of it could be interesting, and is interesting for a square. In this case, we could choose V2 as a pivot point. This is the closest point. The next iteration, we are here. Maybe this is not yet a witness, but one more iteration would get to it. So that's the algorithm. Now, what is the, yes?
Yeah, so in the first case, when the point was inside the triangle, I guess when does the algorithm terminate?
Depends upon how you like it to approximate. In fact, this theorem gives the precise statement.
Okay, I see.
Given epsilon is 0, 1, the triangle in at most these many iterations, these many arithmetic operations, computes a point P prime, which is in the convex hull, so that this gap is bounded by epsilon times this. And this gap, by the way, it makes sense, right? Because you want to measure this gap relative to its distance to the given set of points. And of course, you can, if you do maybe more iterations, you can make this to come to within an absolute error of epsilon. Or if the point is not inside with that epsilon, then you find a witness that says it's outside.
Sorry, what are M and N?
Sorry?
What are M and N in space?
Okay, good question. M and N, the points VI's, that we have n points in the m-dimensional space. So each iteration takes, in the worst case, mn, because you need to compare the distances. But in a lucky situation, you just do O of m arithmetic operation. So it could really be a good algorithm. Okay, so here I mentioned this already. One more remark is that the only thing that the algorithm does is compare distances, two distances. But if you square the distances, you don't need to do any square root operations. So we can do it with elementary operations. Carry out the algorithm with elementary, in step 2 as well, which is the step that finds the closest point. Okay, are there similar algorithms to this? Well, the only one that I have found in the literature that has some resemblance to this is really none. I mean, there's no algorithm, but one that resembles this is maybe what is known as the sparse greedy approximation, which is an algorithm for minimizing a convex quadratic function over a simplex. This is called sparse greedy, and it happens to coincide with something known as an algorithm known as Frank-Wolf, and also something called Gilbert's algorithm. But really, these are all algebraic, what I call algebraic algorithms, as opposed to the triangle algorithm, which is purely a geometric algorithm. I mean, you could say that simplex method is a geometric algorithm too, but not like this one. Because in simplex method, you need to solve linear systems. And you can't say solving linear systems is a geometric problem. It's algebraic. You're doing these elementary operations. Anyway, maybe that's a philosophical point. But we can convert this convex Hull problem into a minimization of the convex quadratic, but that would destroy the geometry and would probably make it run slower.
I have a question.
Yes?
In your triangle algorithm, had you not found the point that was furthest away, if you just found one exception, one point in the such that there was a corner vertex that was farther away, and just used that, A, would it work, and B, would it maybe be faster?
You want to have this triangle inequality satisfied. I mean, you want the distance to be bigger than
right, but not the max distance.
Not the
Well,
max.
you didn't necessarily pick the max distance.
Sorry?
Did you in the algorithm pick the max distance?
No, I don't. I just
any
use one.
Just use one.
That's right. Just
so
one.
Terminate one.
From the complexity point of view, that's right.
Okay.
You're right that you could say, well, let's look at all of them and pick the best one. But that may be, but you may end up doing more work that way.
Right.
Yes.
Could you show us how, if you start with 4 points, you use the triangle algorithm? You said that you can do that, right?
With 4 points?
That you use the triangle algorithm with 4 points.
Sure. Oh, you mean put another point inside?
No, you said that
Okay,
even if you have
like
4
this?
points, you said you still end up using the triangle
okay?
algorithm.
Like that? Okay, so let's say they're here. Now, say this is P. I pick a point P prime. Now I need to find one so that this distance is bigger than equal to this distance. Here I can use this. I find the closest point. This becomes the new iteration. Yes. And I repeat this process.
Thank you.
So each iteration, in the worst case, takes O of mn arithmetic operation. But if you're lucky, it only takes O of m. And this makes it fast, even faster. I mean, while the other algorithm, I think it takes O of mn, the sparse greedy. So I really feel that this is a better algorithm than sparse greedy for solving this geometric problem. But I don't really have any serious computational result at this point. Now here I like to state a duality, what I call distance duality, that says precisely one of the two conditions is satisfied. For each p prime in the convex Hull, there exists a bj such that this inequality is satisfied. So there's always a pivot point.
That P prime could be in the boundary too?
That's if it's inside.
Or inside?
If it's inside, you can always do that. And two, there exists a P prime such that the strict inequality is satisfied for all I. This is a witness. It says, I see it, it's outside. Furthermore, 1 is valid if and only if P is in the convex hull. And 2 is valid if and only if P is not in the convex hull. So we can find a witness. Here is a picture that really tells the story. You take a point, say you have P inside. Take any point inside the convex hull. Look at the Voronoi region of P with respect to this 2-point set. The Voronoi region of P is everything that is closer to P than to P prime. Now that Voronoi, the bisector of this line segment, orthogonal bisector, must necessarily have one of the V's on its side, which means the other one is farther away, so you can get closer to it. On the other hand, if you're outside, you can find a point inside, so that when you connect it and look at the bisector, this Voronoi cell of P will not contain any of the VI's. It's a very simple, really, proof. And the corollary of this is that really a new problem, what I call intersection balls property. Actually, this problem came up in the context of research that I started with a computer science student, David Menendez, and a math graduate student, Ross Berkowitz. And we have, in fact, a paper on something else that is not related to this convex hull, but it's called forbidden zones. But that's another story. So suppose that you take a set of open balls. Assume that there is a point in their, they have a point in their boundary, common boundary point. Let S be the set of centers. Then the point P is in the convex hull if and only if this intersection is empty. I will show you, and this gives rise to another problem, which I call it sort of a geometric dual to the convex hull problem, where everything is defined in terms of balls rather than convex hull. So suppose that there exists a P in the common boundary of a set of balls. Determine if this intersection is empty. Here is a situation where I would be curious if, as mathematicians, you've ever come across this. Take a triangle, take a point inside. Draw the circles of radius at the vertices, with center at the vertices, and radius the distance to this point. These circles, as open disks, they have empty intersection. Okay? And this is if and only if. I mean, I guess people must have noticed it, but we ignored it, or it wasn't useful to us. Here is a situation where the point P is outside. When the point P is outside, if you look at these balls, they intersect at more than. They intersect. And this intersection is actually a region, convex region, supposed to be gray here. All these are witnesses. Okay? So if you pick a point here as your P prime, as the Spider-Man, and connect to P and draw the bisector, you will see that P is not in the convex hull. So there's a geometric visualization of that theorem. The characterization theorem is a characterization of the witness set. WP, set of all witnesses, i.e. all the points such that this strict inequality is satisfied. Then P prime is in the witness if and only if the orthogonal bisecting hyperplane of the line segment that connects P to P prime separates P from the convex hull. A corollary of this is actually this interesting from a computational point of view at least. Suppose that the point is not, P is not in the convex hull. We may still be interested to find the distance between P and the convex hull. Actually, that happens to have applications in machine learning, I found out. So suppose P is not in the convex hull, and let delta be the distance, which is the minimum of the distance as X ranges over convex hull. Then, when you have a witness, you already have an approximation to this distance, to within a factor of 2. So again, it's a fact. You can think of the triangle algorithm as an algorithm to estimate this as well, when the point is not inside. Okay, so reduction of the gap. I don't have time to spend too much on the proof, but this is one of the key theorems in the analysis of the complexity and the performance of the algorithm, which says that if you pick 3 points, P prime, which was the iterate, and V, that was like the pivot point, this inequality is satisfied. If you look at the present gap, call it delta, the difference between P prime and P, and call the new gap delta prime, after we did one iteration, then this relationship is satisfied. So we can bound the gap in terms of this. And in fact, using this, so this is the situation. This was P prime V. Here is P double prime, and it's a comparison of these two. In the worst case of it, really, to analyze this, I consider it a high school geometry problem to prove that. Now, suppose that I want to solve Ax equals to B, x bigger than or equal to 0, which is the feasibility problem in linear programming. It's not a convex hull problem, right? Because it doesn't say summation of xi's should add up to 1. However, if we know that this is empty, this set, which is called the recession direction of omega, then we can convert this problem into a convex hull problem. It's as if you put a new variable here. You put a new variable alpha, and then just check whether or not 0 is in the convex hull. So it's not really that much harder, and when it's not when you don't have summation of xi adding up to 1. And to solve this problem, I suggest what I call a two-phase triangle algorithm, where in the first phase, we try to find if 0 is in the convex hull of these. I know that it's not, but I do the algorithm until I come up with a witness with respect to this. Once I have that, then I use it to decide to what accuracy I can solve this problem, convex hull problem. So I go to the phase 2 of this algorithm. And this theorem is a little bit long, that says now, given epsilon 0, to compute an approximate solution x0, such that this accuracy is satisfied, you use this number, delta 0 prime, becomes an estimate to the closest point in the convex hull of, to 0 of the convex hull of the columns of A. And the bottom line is that we can solve it to within this much accuracy of epsilon 0 to the minus 2. These are in detail, are in my article. But here the point is that this theorem says to what accuracy should you solve when we have the situation Ax equals to B. I want to solve Ax equals to B, x bigger than or equal to 0. And all I do is I introduce an alpha here as a variable and try to see if Ax minus alpha B is equal to 0. And I could artificially introduce the summation of xi plus alpha to be 1, because this is a homogeneous system now. And then the question is, to what accuracy should I solve this? Because I want to divide by alpha eventually. I don't want the alpha to be too small. So, but here we have an estimate of that. Now, solving ax equals to b. Here is the original problem, let's say, for the purpose of this talk. I want to solve ax equals to b, where a is an n by n